So, now I'm recording. Thank you. So, and then of course we have to look at the quality of these models and how we fight overfitting. First, before we do linear regression, let's start with another approach which is older, which is interpolation. What is the problem with interpolation? Well, you're given a set of points. Let's say we're given 2 points here, let's say in a two-dimensional Euclidean space. 1 point here, 1 point there, and then you linear interpolation with a polynomial of degree 1. Well, that's just a line, a straight line, and that would just be a straight line through these 2 points, right? This is the simplest thing you could do at all, in a way, in order to hit these 2 points and then predict what the value should be on other points. So if you have a certain x value, for this x value you predict this y value, for this x value you predict this y value, and for all other x's you would predict values in between. Now what do you do with if you have not given 2 points but n points, then interpolation says you can always, for n given points, fit a polynomial of degree n minus 1. And this polynomial will hit all the data points. And it's very easy to define, because basically what you say when you have these data points up here, you always have this term. And for this term, you always say if my x is exactly the value of xk, where xk is one of these, then this becomes 0. And so I multiply with 0, and then I will have exactly 0 contribution. And this I do for all the case other than the xi. And only if I have exactly here an xi, then I don't do this, and then I have a 1. And for this value of 1, I will multiply it with the value of my yi at this given point. So if you do this exercise for x1, you will see that if you put in x1 here and do all the rest, you will exactly return y1 and nothing else. And by this way, you, for example, here for these 8 points, you interpolate with a polynomial of degree 7. This polynomial hits all the data points perfectly and gives you predictions for other values. Now, why is this maybe not a good solution? Exactly. So the function is oscillating. It's excitating in a lot in the different directions. And as you add more data points, more observations, the formula gets more and more complicated. And because of the oscillation, it's unlikely that you will do a good job in predicting the function. Because usually what your underlying assumption is in machine learning is that your function should be rather smooth and not excitate wildly in all the different directions. So it is unlikely that if you're given these data points, you really want to have such a high value here, given that the values here are really close to each other. And also when you extrapolate, you see this will go very steeply as you increase on the x-axis. Likewise, it goes up very quickly as you decrease on the x-axis. So such an interpolation typically is not a good way to fit a curve. And that's what we're doing here all the time in machine learning. When we do regression, we're fitting curves given observed data points. So this is oscillation is a problem, instability is a problem, even numerical computation will not be nice when you have a million data points. And it's usually implausible for generalizing to unobserved data. Although you will hit the observed data perfectly without any mistake. Still, the generalization to new data that's not been observed will likely not be very good. Now, what could you do? What are other alternatives? I mean, people in interpolation have thought long and hard about this. You could do, here's the simplest approach, linear interpolation. Let's just go from point to point and always say there's a straight line in between. Actually, in terms of doing a prediction, this will already be much better than the approach before. It's not so nice because, for example, here at this point you have, you're not smooth, right? The first derivation will be different as you approach this point from the left versus you approach it from the right. And so the interpolating curve that we get here is easy to define. We basically just say, if we have an x that is between these 2 points, we just take the linear interpolation between these 2 points. The model also becomes larger and larger and larger as you observe more data points. Again, with 1 million data points, you would have 999,999 such interpolating linear equations, and that's also not a very compact model. And when you have an outlier, then of course your linear interpolation also goes wildly with that outlier. So we always have some problems with the data observations, so being robust against outliers is a key property we want to have from our machine learning algorithms. Now, what else could you do? You could do, for example, spline interpolation. That's a little bit more refined compared to linear observations because you do the same thing as before. So you have some curve between points that exactly hit the points. But in addition, you require that the first derivation from the left gives you the same as the first derivation from the right around all these different points. So basically what you do is you pick polynomials of lower degree and make sure that they agree at these points with the first derivation, maybe even with the second derivation. You can choose that. You don't get then a polynomial of degree n-1, but maybe you have piecewise polynomials of degree 2 or 3 as you like. This is often quite effective, has been done a lot in computer graphics. There are different kind of splines that are defined in different ways, and it's very useful. Again, it's not necessarily smooth with higher derivations, and we run again into the problem that for many data points, like thousands, millions or more, the model will be super complex and hence will not be very efficient in doing inferencing. What's the issue with not being smooth? It's a good question. I like this. In general, you would try to come up with a prediction that is as close to reality. Now, quite often, you could say, of course, if reality is not smooth for my functions, then maybe it's a good idea that I don't have a smooth function here. But quite often, what we observe are natural phenomena that are smooth in some way. And not to assume smoothness typically would require an underlying mechanism. And even then, we would have to understand where this underlying mechanism would be non-smooth. Let me try to rephrase the same thing what I just said with slightly different words. Usually what we try to model are phenomena in physics, or phenomena in how people interact. And these phenomena, they generate data. It's not just that data is somewhere, that there is no reason for that data, but there is a data generation process. Very, very often these processes are smooth. So then when we know that these processes generate smooth data, we want to use this knowledge and have our model be likewise smooth. Even if the data which produced this is not smooth, there is still the question, how can I best fit my data? And even then it might be better, perhaps, now I'm speculating, to say I want to have like a smooth continuation over these observed data points. But it's a very deep question, yeah, like what is the property of my data generation process and how can I put this knowledge about this data generating process into my models? And this is where, for example, people currently do a lot of research, like in physics-informed machine learning. They try to put further knowledge about the physics into the generation of curve-fitting functions in order to produce the best functions. Not only based on data, but based on further knowledge about what caused these data. And of course, we would still overfit to outliers, because if a point here is by some random procedure up there, then we would, of course, still exactly hit this point. So there are other interpolation methods, more sophisticated than I want to show here. And I really show these interpolation methods only in order to give you also a sense for why you may not want to use interpolation in such points. I mean, these methods like Gaussian processes are used a lot also in machine learning because they give you further information that's super interesting, and also others like Fourier, trigonometric interpolation, so they're very useful methods. But now let's get to linear regression instead of interpolation, with the idea that we have noise in our generating processes. Yeah, again, there's a data generating process, could be a physical process. Maybe that's even a perfect process, but then we observe the data and the measurement includes noise. Even if you take a yardstick, apply it, and you measure the same thing several times, you will not measure exactly the same length. And of course, this is true for many measurement processes. We want to have a simpler model, because we want to generalize to unforeseen data. And if you think of physical laws, like force equals mass times acceleration, the beauty of that law is that it is so simple. And when you think of how did Newton come up with this law, I mean, when he measured an apple dropping down or so, he certainly will not have observed exactly this law, but rather his measurements error of like how long does it take the apple to drop down will certainly have not hit the data precisely. So, but he decided to go for a simple model, and this simple model proved super powerful in making predictions. Simple does not necessarily mean simple in terms of finding the model. I mean, we can have all kind of heavy machinery in order to find a particular model. Okay, now linear regression comes from statistics, and statisticians correctly say, what did machine learning invent? We have been doing linear regression for 70 years or longer. I don't even know, I have to say, but maybe even 100 years. So it's not a new technique that was invented by machine learning, but has a very long history in statistics. Statistics typically work a bit differently than machine learning. Machine learning often just looks at, well, can I fit the curve, and then how good is my performance? Statisticians rather care more about the data generating process. And at the other hand, they're typically empirically not quite as good when it's about doing predictions. But that's a different story. But I know from, for example, former PhD student who went to an insurance company, that then they are not quite used to the machine learning procedure of doing rigorous testing with k-fold cross-validation and so on. But what do statisticians get really, really great is that they have a principle-based approach to building models. So what they start with is not the solution, but they start to think about a problem saying, what if I have a function? And this function produces data. And that's what they do. So they say, okay, what if I have a function? Then the function is this data generating process, a physical process, a social process, doesn't really matter. And this process generates data. So I put in an x and I get out a y value. This is the data generating process. This is where I start with. And then I produce data. And the assumption for linear regression is that I have such a function. I have this red line first. And then this process generates data points. And it does so according to this function. But there is noise on top of it, whether that's measurement noise or whether that noise is built into the generating process. So if you take a social process and I try to predict, for example, how fast you will be at solving a mathematical equation, I would expect that at least in a certain age range, you will get faster and faster as you see more mathematics and get more practice in solving it, right? So I would have a model, and this, of course, whether you solve the mathematical equation would still be up to noise, whether you had a lot of partying yesterday or whether you slept well and you could really focus your mind on the task. So this is best model as additional noise. So these data points are created by this function which underlies the whole thing, which produces then these observations. And then the statistician says, okay, I observe now these blue points and I don't know the red function, but I want to recover the red function. And now, given these assumptions about the noise, for example, the noise that is assumed in linear regression is supposed to be centered at my function. So the epsilon that I add has an expected value of 0. And I assume that it's normally distributed. So most of the noise will be close to the bar, very small. And there will be very little noise that is down there somewhere. So it may happen. So what they basically say is that the generating function is then eventually some linear dependency from some input variable or predictor variable plus some bias in terms of offset from the 0 point here, plus some noise which changes every time I put in an input variable value. Now, for this key principle that I have such a generating function, there are now variations. The variations basically are about going from few dimensions, like here I had just one predictor variable, that's my x, and one response variable, that's my y or f of x. I mean, yeah, one-dimensional input, one-dimensional output. That is simple linear regression. Yeah, one predictor variable and one response variable. And this is, of course, terminology you need to know. You can also have multiple linear regression. Then you have several predictor variables. So your input vector here is a vector and not just a scalar. Yeah, so you have a dependency on several inputs. If you try to predict the weight of a person, maybe how tall and how broad and how deep the person is might help you to estimate that. And you have one response variable. And then you have multivariate linear regression, and then you have several predictor variables. So every input is a vector, and you even have several response variables. So you have a whole vector of responses. So you do not only try to predict one value, but several. For example, if you try to predict some direction of a car, you would want to indicate x, y, and z velocity. So that could, of course, be, in general, 3 different velocities. And you need all of them together to know in which direction the car is moving, how fast. Okay, so let's now do multiple linear regression model for multiple observations. Of course, we won't have not just one data point, but a large set of data points. And we want to learn, the statistician would say we want to infer the function that most probably underlies the whole system. We want to recover the red line that I showed you before. And the statisticians, they make nice proofs. If you have infinite amount of data, you can recover this line perfectly. We never have infinitely many observations, of course. Our data set is always limited, so there will be some problems. But let's get to that later. Okay, so we here assume we have one response variable per observation, per data point. And, well, there's always some random error involved, as I said already. Expectation of the random error is centered around 0, and it's Gaussian distributed, normally distributed. And then the yi depends on a vector of inputs. And then the linear function involves parameters beta 1, beta 2, up to beta d. This corresponds to the number of the variables plus 1. And then the goal is to estimate these betas. For example, to study their relevance, which beta is large, which is small, and also to estimate the error that comes with these betas. By the way, errors are also called residuals, and the predictor variables are called also independent variables or input variables. Especially in the social sciences, people like to talk about independent variables. These are the ones that you modify, and then there are the dependent variables. The y's are the dependent variables that react to the independent variables. So what we try to do now is exactly this. We have data points, and now we try to find the function that seems to be a best fit according to these data points. And you see, I mean, it's not always a very good fit. Like in this case here, right, you see the data points describe almost a bit like a U or an inverse L-shaped form, and we just lay a straight line through that. This is, of course, an important observation. Here we can always put a straight line through our data points, always. The mechanism will always give a value, a function back. Whether that makes sense, that's another question. And you always have to check whether it makes sense. Okay, so let's first look into the scalar representation, and then later on I recommend you to really learn the matrix notation. But just so you have a smooth entry, let's first look at the scalar representation. The scalar representation says for a yi, I have, this is predicted based on some beta 0, that's the bias or offset, plus beta 1 times the first component of this x vector plus the dth component of this times the dth component of this x vector plus some noise, and all together this gives us the y. Be careful. Sometimes when I ask this in oral exam, yeah, then people tell me this is the function or that we know about this noise, and of course we don't know. Right? We assume there is a function that has this noise, but actually, in reality, we don't know it. We just see the data observations. We see for a given xi, we see the corresponding yi. That's it. Now, this is a little bit bothersome to write. Takes too long, especially if we have large vectors. So let's write it in a vector representation. So the yi, this is still a scalar here, is nothing else than xi transposed beta plus the noise vector. There is a bar over this xi. What does it stand for? Well, we have here this beta 0 that doesn't have any x component with it. But what we can easily do is we can write for every xi that we have, we write here this xi and put a 1 in front, because when we then take this vector and multiply it with the beta vector, then this is simply 1 time this beta 0. So this is a small technical trick to make this a very nice expression that's short and sweet. Okay, so our yi is then simply xi transpose times beta plus some scalar, which is the noise for this particular observation, which, as I said, we don't know this noise. And this is how we try to model our problem. Again, we assume there's this underlying true function. Yeah, be aware that this beta is also a vector. This epsilon in the very end will also be a vector. Here is one component of this vector of random noises. Now, very often, of course, what we have is then not just a single observation. A single observation corresponds to one such vector. Typically, we have many observations. Yeah, we have 1 million data points. So we have 1 million such vectors for which we also have the response. So rather than writing this line 1 million times, we just organize these vectors in a matrix. Well, if all of these xi's were vectors, then x transpose is a row. So we have one row and the next row up to the nth row. So for n data points, we now have n many rows. And we have d dimensions plus this additional 1 because we have this bar. So d plus 1 many dimensions per row. And then we have n different data points. And we write this as a matrix. And now if we write the y also as a vector of y1 to yn, so for each data point we have a response, we can simply write y is this matrix times this vector of parameters that we don't know yet, plus epsilon, where epsilon is simply the vector. For every data observation, we have some noise that initially we don't know. Well, so now, isn't that nice? We write this vector is this matrix times this vector of parameters plus the vector of noise. And with this, we capture then even 1 million observations in one sweet equation. Yeah, so that's, I think, very beautiful. And this is what we work with. Y is x times beta plus epsilon. Now we have our challenge. The challenge is we want to recover the underlying function f, the red line that I showed you before. Now, we don't know where the red line is. Now, what can we do? What we can do is we can say we can produce an f hat, and the f hat of x is x transpose beta. We don't know the epsilon. We cannot predict what the noise will be for any particular observation. So we just say, let's recover the underlying red function I showed you, and let's assume there is no noise on top of that. Because, well, how would we know the noise? It's the very definition of noise that we don't know it. Otherwise, it would not be noise, but it would be some systematic behavior. And of course, when we find this function f hat, then, I mean, we could, of course, produce many functions. So if we have some data points, we could offer a function like this. Probably not a good idea for these 4 data points. I would rather maybe have a function like this. So how do we compare the functions, how good they are? Well, if we have a good function, then it will produce a smaller deviation from the actual observation. Or we could say that if we then observe the difference between our prediction and the true value, then the difference lies exactly in this noise, and we want to minimize this noise. And rather than saying we want to minimize the noise, we can also say minimize the squared noise contributions. And when epsilon is a vector, then epsilon transposed epsilon is nothing else than the sum of squares of these arrows. And by the way, I used here now f hat because often I like to use the hat notation to say this is what we want to find, or this is what we find, and this is not the true underlying function. The true underlying function we tend to write without a hat. But quite often, especially if you look at literature, I mean, there's a tendency to do it like this. You will just see this. And instead of the bar here, you often just see x. But, I mean, in the right context, you know what it means. Okay, so now the question is, we understand the process. We have this linear function that produces data plus some noise, including some noise. And now we want to recover that function, and we want to minimize the epsilon. We want to find one where the noise is as small as it could possibly be. So how do we do this? So, well, we define now a loss function. The loss depends on the parameters that we assume. Let's look again. Here, this is our function, and this is the beta. The x's we know from our data collection. We have x1, x2, x3, and for every x1, x2, x3, we have y1, y2, y3, and so on. So, the loss function really depends on the beta that we choose. Yeah, and conceptually, we could say, oh, we try any value of betas that's thinkable. So, the loss function, as we said, is nothing else than the sum of squared epsilons, and these epsilons depend on beta. And how do they depend on beta? Well, I go through all data points, I equals 1 to n, and I always look at my true response and subtract the predicted response. And this predicted response depends only on beta, because remember, xi and yi are observed data points. Yeah, so here I really say this is the residual that my current parameterization of my f hat does not acknowledge. So this is supposed to, and I square this because I decided to do the squaring here. And well, I can rewrite this. Instead of this, I can rewrite this in vector notation. This is the same. Instead of going through these data points, I write the vector y. And for each component of y, I subtract this part. So directly I can write instead of y minus the matrix x, which the matrix x has all these rows. And the beta is always the same. And to get the square, I take this component and multiply it with itself. So this is just a rewriting. And this is nothing else than y minus x beta squared. So this is just a different notation for the same thing. Okay, this is now my loss that I have. And remember, we want to have a small epsilon or a small epsilon square. How do we do this? Well, we take analysis. That's what we use a lot in machine learning. We compute the first derivation, because if you remember analysis, at minimal points, the derivation is 0, right? You have that the derivation at this minimal point is 0. Of course, this is also true for the maximum, but the way we construct it, we will find that we always find a minimum by this method. So we compute the first derivation of our loss function depending on beta, because what we want to do is we want to vary beta to be at such a point where our function is minimal, describing a minimal noise vector. And now if we take this here, or this, and just apply our derivation rules, what do we get? Well, we have the inner function, which is squared. So this is then 2 times this inner function. This is here the inner function. And then we have to derive the inner part. The inner function, depending on beta, means that this is a constant. And this is the variable that we are interested in. So this is the inner derivation, is x, and we put the minus in front. So the derivation, according to this vector beta, is exactly this formula. You see, what we did, of course, was we didn't really care much about the fact that beta is here a vector, we could just write it very easily in this way. That's cool, because now we have the derivation of our loss function, and what we can do is we can set this to 0. Here's just an intermediate. Yeah. Let's move back to so here we have we have this y's and we have the x's. Yeah? And given our y's and x's, these are our observations, we want to find betas. So conceptually, you could think, put in any beta you like. Compare all the beta vectors that you could ever think of. What would be the best beta vector? What would be the best parameterization? The best parameterization would be this one, where you take y minus x beta, which gives you epsilon. And this would exactly be the noise that you have. What you want to do is you want to say, if this was the right underlying function, it should have very little noise. And if I compare two functions, and one function would assume a lot of noise, and the other function would assume very little noise, then the one with very little noise would be better. Okay? Okay, thank you for asking. So now we have this derivation. Quick intermezzo. Yeah, please. Yeah, so you are right. So when we have a function like that, and we find that the derivative is 0, we don't know whether it's a minimum or whether it's a maximum. Yeah? And then with the second derivation, we can find out to which it belongs, whether it's minimum or maximum. Here it's quite simple, because we have this epsilon square, which is a parabol-like shape, so we know already that it will be a minimum. But in general, you're right that if you know nothing about the function and how it's composed, then you would have to compute the second derivation to decide whether it's a minimum or a maximum. Okay, so just as an, yeah, another question? I fear you really have to shout. When you are here, right? This we're just working basically with scalars. I mean, this is a vector and this is a vector, but this is then a scalar, and so on and so forth. You have to figure it out such that everything works out to represent this. Yeah, this is basically, and when you then again think about this, yeah, you have to figure out that it really works out, but you can try at home. It really does. Okay. And by the way, since this will be values in the end, quite often what you can do is you can, for example, put this on the other side and choose the other transpose. When you have a matrix and you have the information content of a matrix, it is rather up to you to decide how you organize the matrix. So basically, what side is up? It's for you to decide how you do it. You must be consistent, of course. Okay, so just a small intermezzo about derivation rules that we will also need in further course of this lecture. And this is just a rehash of what you had in mathematics anyway, nothing new here. So if you do exponentiation and you derive according to x, it's n times x to the power n minus 1, so that's what we just used, as long as n is not 0 here. We have the sum of two terms that are derived according to this dependency of x. Then you just derive the two terms and add the sum here. If you have a product, you have the product rule. You have one function times another function. You take the derivative of x. This is the derivative of g of x times the value of f of x plus, and here you derive the other part. And then there's a chain rule, which we need a lot also for neural networks. If you have g of h of x and you are interested in the derivation of x, you do this in two steps. You derive g of h of x according to h of x, and then d of h of x according to x. And sometimes this part is also just written as d of d of g of z with the derivation of z. I mean, that would be an alternative of just writing this part here. Now you can just say instead of h of x, I write a value set. And this would be the same. And quite often when you write it, when you have one dimension, it's clear you just write prime or you write these dots just as alternative notations when the dimension is clear. For example, people like to do this in physics, where often you derive according to time and not to space. Okay. Yeah, some more rules here. What we need are partial derivatives. Well, what does partial derivative mean? It means that you have more than one dimension that you derive, and then you can derive first according to x and then according to y, or the other way around, but this is commutative, so this doesn't matter. And here are some examples. You have one function of x and y, you derive according to x, and then you end up with this term, which is no longer depending on x in this case. And you can also take the very same term as an input and compute the two partial derivatives, first of x and then of y, and then this is this term, and which is again derived according to y. So a partial derivative is just a derivative in one dimension, and you can repeat this several times. And we need this for multidimensional problems when we want to optimize in a space and optimizing a vector that targets a particular direction. Okay, so this was the loss that we had, which depends on beta, which was this function. And now what we do is we set this to 0. Remember, this is basically this is a vector as a result, and this is a 0 vector here, and has the many dimensions. And this, of course, gives us a linear equation system. Now we can work a little bit to resolve this for beta. So we write it like this, just multiplying here. Then this is the same as this. And if we now solve it for beta, we get a beta. And the beta is just, we bring this part to the other side. This is this part. And then we multiply on the left with x transpose x to the power -1. I mean, we have matrices, so we cannot divide, but we can take the inverse of a matrix. And the inverse of a matrix times the matrix itself is then the identity. And so if we multiply with the inverse times this term, then this becomes the identity, and we have beta left. And overall, this gives us this beta is this. Now, which beta is this? This is a particular beta. It's the beta that corresponds to the beta for which we have minimized this epsilon vector according to our least sum of squares. And this also is described here with a hat. Why? Because it's our predicted beta. Why is it predicted? Why is it not the true underlying beta? Any idea? This is now a crucial question to understand. Why is this not the true beta? Why is it just the predicted beta? No, we are there. We have now computed the best beta that we can do. Not quite. Let's assume it is linear, because all this is done under the assumption that our data generating function is a linear function plus some noise. So that's basically where the statisticians go in and say, let's assume this holds. But even when we assume that this holds, it's not the perfect beta, at least usually. Or noise can distort it. Yeah, that's one component, and it's not sufficient. We have yeah? Yes, this is the point. We have limited data observations. So, if this is the true function, now let's make it extreme. Let's make it, we just have two observations. Maybe the observation is like this and like this. Now, what is the best beta now? The best beta would correspond to the line that goes exactly through here. And this, of course, would correspond to the beta hat, the best one that we could find. But why is it so poor? Because our data observation was finite. Well, in this case, very finite, because we had just two. That's extreme. But it's the same is true if we have 1 million observations. We never have a perfect representation of our true underlying function. So this true function would have beta. And if we had infinitely many data observations of this data generating process, then we would recover it perfectly. But since we never have infinitely many observations, it is super unlikely, basically zero probability, that we recover it perfectly. And this is exactly where overfitting comes in. We overfit to our data observations. Here, very obvious, because we just had 2 data points, but it doesn't matter if we do 10 data points or 100. We overfit to our sample, and the sample comes from this sample of all possible observations, and this is random, and therefore also we will always have a random deviation from the data generating function. Okay, then the other thing is, here we have the analytical solution, and in oral exams I always ask for this analytical solution, well, not always, but very often, because this is about really understanding this process. And I do not just ask for the final result, I rather ask for how do you compute this final result? Yeah, because I want that you understand what are the assumptions and how, given the assumptions, is the mathematical machinery to derive this result. I don't care so much that you remember from your memory how it's done, but rather that you can do it yourself. And since, and the problem, of course, is computing the inverse is a mathematically intensive computation, especially if you have 1 million data points. So this would be then a 1,000,000 times 1 million matrix. It's not so nice to have. And so rather, people use stochastic gradient descent to find the minimum. And we will look into stochastic gradient descent in general later. Okay? Okay. So now we have this wonderful method. But someone said already, what if we don't have a linear underlying function? Are we lost now? And the good thing is, no. We can do more than just purely linear functions. When we talk about linear regression, the question is, it is linear in what? Is it linear in the effect of parameters? Yes, because I multiply with my beta, and this is a linear operation. I multiply with beta, and I add another multiplication with a beta, and I add maybe an offset. But is it linear in the input? no, this is not necessarily true. We can modify our input data. Yeah. I'll explain that, and if you don't know in 2 slides, then please come back to ask this question. Okay, so we can do linear regression on nonlinear features. And I will show you several examples here. Polynomials piecewise. And the features are now object descriptions. If we have an object description, yeah, often this is a vector x. Now we change this x and turn this x into something else, namely a feature vector. So we take these inputs, xi, these are scalar, these are vectors in R to the power d, and we replace them by some nonlinear features. So we take any feature function phi, and then we take phi of xi, and this gives us a new vector. So this vector, remember xi was in d-dimensional space. Phi of xi is in k-dimensional space. K may be lower or higher. Typically, k has more dimensions than the d. And what I do then is I say my y, this is again observed data. Yeah? I have my data input of x's and y's. So y is observed data. I put my x's into this feature function, and here I say already the feature function delivers a k-dimensional result. So I have different components for my feature function. And so what I do here is I have possibly different feature components that I compute from my input vector x and multiply them component-wise with the corresponding parameterizations, plus I have some noise. And I can write this more elegantly here as phi of x transpose times beta, where phi is a vector and phi of x transpose, is a vector. And this phi does something funny, weird, whatever I like it to be, multiplied with beta, and I assume there is further noise. And then my matrix is no longer consisting of x1 up to xn, but it's consisting of vectors phi of x1 up to phi of xn. And these feature vectors here are formed through an arbitrary set of feature functions that I choose. And what you see from this part here is then, from here on, once I have turned x into phi of x, I use the linear process. I don't change anything of what I told you before. The only change that happens is that I turn my x into phi of x. Now, why should I do that? And what makes this useful? First, let me show you how this could look practically. For example, here I have my original input, and remember the original input is also like a phi of x. It just has this one and then all the different inputs here. This is my linear feature vector. Now I could have a quadratic vector which would have the 1 and the x1 and all these components, but it would also include an x1 square. It would also include an xd square, and it would include all the multiplications of the different components. So what I do here is I take the original one and I extend this original vector of x by additional values that correspond to squares or multiplications of my components. So I have now more possibility for learning betas and trying to predict the y. So here, in this particular case, I now have not a 1 plus d dimensional space, but a space that has 1 plus d times d plus 1/2 many dimensions. And of course, I'm not limited to quadratic. I could do the same thing with cubic. And of course, I get an even higher dimensional space. And so this vector here, through the working of phi, becomes this vector here. And from here on, I ignore that I have done something like that and just compute my betas in order to have the best betas for this specific case. And why is this good? I'm missing here a slide that does it nicely. Well, let's assume we have data points that are a bit like this. If I now would do a linear regression that only has linear components, the result would be something like this. This would be my beta hat, or the function corresponding to the beta hat rather. But obviously, when you look at this as a shape, what does it tell you? It looks something like a quadratic function, right? Now, with this method and the quadratic phi, I do not only return x1 for being multiplied with some beta, but I also return x1 squared to be multiplied with some beta. And by this way, I can learn to which extent I should have an x1 square. And with this, I can predict a regression like this. Probably not so nice quadratic function as I would like it to be, but I think you get the point, right? So by throwing in these additional values, and of course I do this for all of these points. I do this that I throw in the corresponding x1 value and square it also. And so I can learn any kind of quadratic functions when I do this expansion according to this quadratic phi here. And the same is true if I have a cubic function. I could learn this cubic dependency. I always have the problem that my models get more and more complex because I learn then eventually some polynomials with this purely linear regression technique. Now I can do even much more. I can do very fancy stuff. For example, what I learn here, this corresponds to this piecewise constant behavior. I can cut up my space. Let's say I cut it up here along the x-axis, and let's say the true underlying function is the blue one, and I now learn piecewise constant behavior. Well, piecewise constant is a very simple function. The very simple function is always described by basically components, and these components, when I put in, let's say my x would be here, I put phi j of x here, then this here expresses a condition, and this condition returns a 1 if the condition is true. So if I'm here, then for this part, a 1 is returned, and for this part, I learn a corresponding beta. And what I then do for this part is I learn a beta that describes the height, which is the average of all these data points here which are observed. If this beta is here, but my x is here, then this condition says here this is 0. I don't have to care about this. When I'm here, I learn a corresponding feature function, and this feature function is only 1 in this part of my x-axis, and I learn a 1 here if I'm in this part, or I predict a 1 if I'm in this part, and then I learn a beta that describes this height. And so for these observations, these dots, given by this blue underlying function, I learn a piecewise constant approximation expressed in these kind of conditions. Now we can, of course, discuss whether piecewise constant is a really good approximation. Usually not. But this is like an entry point to understanding what comes now, because I can also learn a piecewise linear behavior. This is described by this one here. This works like the piecewise constant, but it allows also to learn some slope. And the slope is then represented by a beta 0 and a beta 1 for each of these elements. And so now I'm already doing a little bit better for this blue function. Now, here I still have these jumps. I can do still better by saying I'm interested in a continuous piecewise linear. Now, for a continuous piecewise linear, I change this feature function again, and now I return x minus zeta j for the j's feature function component, and I return only the positive part of it. Yeah, so term, square brackets, plus evaluates to term if term is larger than 0 and 0 otherwise. So if it's below 0, I cut it away. And if I do this, you really have to think about this at home with some numerical examples, then you arrive at a piecewise linear approximation where it's made sure that at these points the function from the left and from the right is at the same height. And by the way, for this one here, this is how a piecewise linear basis function looks like. Now, I have to say I have not seen these examples used that often, but I think they're quite illustrative to understanding the principal mechanism. What is used a lot and liked a lot is the usage of radial basis functions. So they play a prominent role in many parts of machine learning, also later on for support vector machines, but also here they are really much liked. So what are radial basis functions? So they are defined around centers. And when I have a center Cj, then phi j around the center of some x is defined by this radial basis function with this center. And this is nothing else than e to the power minus 1/2 x minus the center square. Now, how does this look like? When I do a one-dimensional consideration of this function, this is nothing else than I have here my center. Then the value of my x is close to this center, are high, and further away they approach 0 rather quickly. It's basically a kind of Gaussian distribution, or Gaussian distribution-like. And what do we express here is, we express how close such an x is to a center. And the implicit idea is that when I use a radial basis function, I learn how close my x's are to the different basis functions. And if they're close to the basis function, they are multiplied with a high beta corresponding to the corresponding basis function. So what I express here is similarity with my center. And this is a very powerful idea, because now when I express similarity, if I have sufficiently many centers, I can approximate basically any function. So one thing we can also do is use all training inputs, all the data points we have as centers. Of course, this becomes a very large model, so that's the disadvantage. But let's assume it's not too many, maybe just 100. Then I would have a vector of 101. And for each new x, I would measure what is its closest center. And then the closed centers, they will have an influence on the value that I predict. And that will be a kind of interpolation between the different centers. So this is a little bit like KNN in a kind of continuous regression-like case. And it also works nicely in higher dimensional space. Okay. Now, I think I give you this exercise for at home. Think about this, this slide, and what this slide does is it asks you to do a linear regression and think about how to model the linear regression. There's also an answer. By the way, especially what the radial basis function approach does is that it basically tries to represent data by itself. So in statistics, what people tried to do in the past was to say, I have very little data and I need a statistical representation. Now I work on having a very complicated machinery in order to arrive at a good statistical model. And maybe my model is very complicated. With big data, there was a change of thinking. The idea was rather have a simple model that scales to a lot of data. And then the data, because it's so dense everywhere, represents itself very well. So linear regression with radial basis functions corresponds to that. If you have many feature functions, you can very well represent the data in that area. Okay. Now the question is, how good are our models? Let's think about our model again. What is our y hat? Remember, hat is always the predicted value. So we predict a y, and of course the predicted value, the y hat, is different than the real value. And how is it predicted? It's predicted from x beta. And how is the beta predicted? Beta is predicted from this part. So y hat is nothing else than this part times the original y. And this is why we can also say that the y is projected onto another plane, and the distance from this plane is given by the noise. Now, when we do this, the question is, how good is our beta? So how good is this part? Well, we said before that the epsilon is supposed to be centered around 0 and that it's supposed to be normally distributed. So when we now look at these epsilons between our predictions and the true value, so the true value was from our observation, this was the fitted value. Well, we can also write it like this. Then our residuals, our noise, should not be somehow. It should be fluctuate randomly around 0. So this would be a picture that we would expect that it would fluctuate as we change our values. What would be a counterexample? When we change our y hat and the error that we have changes. So here with growing y hats, the error increases. This would be strange because the epsilons are supposed to be centered around 0 and always have the same kind of noise behavior. So when we get a picture like this noise behavior is not the same for all possible values. Thus, there is somehow a mistake in our model. We also have a mistake. I mean, here the mistake grows linearly. That's strange. Here we have a nonlinear growth of the epsilon with y hat. Here we have two groups, and in this area we have a noise that fluctuates around 0 but has a certain variance. Here it's still around 0 but it's a larger variance. Again, somehow we have some things in our data that are not captured by our model, because if the data would correspond to our assumptions, then it should be like this. It should not be like this, not like this, and not like this. We violate our assumptions. And then, of course, when we violate our assumptions, there is a question whether we can repair it or not. Yeah? Maybe we don't have a better idea what to do here. Maybe what we find is we have two functions. One function is maybe describes this area, and one function describes this area. So, for example, I gave you this example about predicting something about dogs. Maybe we have, here is the Chihuahua, and here is the Bernardina. And maybe there are two functions that underlie these different species, or these different races of dogs, breeds of dogs. And that's, of course, when you model something and you find in your data there's more than what you modeled so far. And maybe you should then correct and try to find a better model. This one here, again, we have y hat here and the epsilon term here, and we have such a kind of behavior. So this points to some quadratic part missing, because if on the one side the error is like this too much and then it's too little, so there is some quadratic term that's missing. Yeah, so the question, just to repeat for everyone, before we checked for quality, for example, with precision and recall. How does this relate to what we do here? I give the question back to you. What would you answer? It's a good question. Yes, exactly. So when we talked about precision and recall and accuracy, we talked about classification. And we will talk more about classification, and implicitly in this whole mechanism there are also like continuous measurements often. But in the end, when we have a classifier, we only care what the classifier says. Let's say it's, I don't know, good customer, not so good customer, or this traffic sign or that traffic sign. When we are interested in the prediction, it's a categorical prediction. So it's a bit cold here, and I can move. Yeah, you're even sitting here. Sorry for you. So it's a categorical prediction, and we look at the confusion matrix to see how one prediction was and should have been different. Here, what we look at, we do a numerical prediction in a continuous space, and what we basically do is we try to minimize the distance between the true value and the predicted value. And this is then also our evaluation measure, that we take the sum of squares of the residuals in order to judge how well we are doing. What I have not done here yet, which you should always do, is I have not split this into a training data set and a test data set. Yeah? So I only have worked right now here on the training data set so far. Sure, when you do regression, you also need to distinguish training and test, and then your quality judgment for regression will be, for example, the sum of squares. sometimes there are modifications for different purposes, of course, but this is an archetypal way of judging the quality of regression. Whether now a certain mistake is a good mistake, so an acceptable mistake, or not, that's then a question that depends on your application. And this I cannot state. Yeah. For example, when you do prediction in launching a rocket, then you want to have an angle which is very close to the very, very, very close. Yeah, when you try to predict a car on the street, you have much more leeway of what you want to predict, and so it depends on the application, what mistake with regard to your angle you predict, whether a particular sum of squares is good or is not good. But you would use sum of squares. Okay, thank you for the question. I think that's very helpful to reflect on what do we do and where do these different building blocks fit. Okay, so here you see we have some systematic variation that is not like the noise is supposed to be distributed, and we should account for this in our model. And here it looks like we should probably add some quadratic feature function to our model. So, what are the assumptions? Some I mentioned already, but some I didn't. So what we assume are that the residuals are jointly normally distributed. And we expect that they are distributed around 0 with a certain variance. We assume usually that the variance of our errors, so the variance of our errors is our sigma square, is constant for all our observations. Now, of course, here we had a counterexample. Here, the variance of the errors was not constant because here the variance was small and here the variance was large. So this would be a counterexample for having constant variance. We assume that the xi's can be observed perfectly, that they are not noisy, so only the process of predicting then the y would be noisy. And we assume that the errors are uncorrelated. So epsilon I and epsilon j would not have any variance. And again, you could say this would be a counterexample because the errors here are correlated smaller than the errors here. And because we have this equation to hold, and the x and the betas are exact, all the yi's are distributed with the same variance as the noise. There is no distribution here, so all the distribution comes from the noise, and the y's are then distributed exactly with the same variance as our noise variables. And if now our residuals do not have a mean value of 0, then we need another model. So basically we are not able to arrange our model in such a way. I mean, in general, for independent observations, I'm not quite sure how we could arrive at that, but surely when you have time series data or so, you might more easily run into problems like this. Because then, when you have time series data, each observation in the next data point is somehow correlated to the previous data point. Yeah, if I observe how a tree grows over time, it will not fluctuate, right? So the tree usually will just grow a little bit compared to the previous data point. And for violations of the other assumptions, there are generalizations. So there are generalizations which we do not talk about here. There's a rich set of statistical literature that varies assumptions and produces then corresponding results. Now, when we do this linear regression analysis, we may have different objectives to do so. The one thing that's typically the statistical thing is to find a good fit. So find a hyperplane over our predictive variables to explain the responses such that the errors are small. I mean, that's what I described to you as an underlying rationale. Now, a good fit would mean I try to reconstruct a very good function which is good compared to the original function. I might also have the goal to have a good parameter estimate. Why might this be of interest? Why do I want to estimate the parameters beta very well? Yes. So let me repeat what I have understood parts of it, but the part of it I understood that it was correct. So when we know the betas, we know which part of the x vector influences our outcome. We may learn that some betas are 0 or close to 0. Right? That they're exactly 0 is something we will learn only infrequently. Even just by statistical fluctuations, they will usually tend not to be 0. But if they're close to 0, there's no influence of them. And that's also useful for us when we put in these feature functions. We may learn that there's no quadratic term in there. So that's good. And then this may inform us, and maybe that's all that we care about. We only care about the strength of some combination of the x input and the y output. Yeah, so you might want to predict, as is the task in one of these slides, what are the parameters that make you earn a lot of money? What do you need to change? Do you need to change your hair color or the color of your sweater, or should you change the company and become manager? Yeah? So some of these may have a 0 influence. And so you care about how strongly this is. And of course, again, in the social science, you care a lot about the strength of these correlations. Good prediction. You try to predict a new response as a function of new predictive variables. Do you have an idea how this is different from the good fit? This is a hard question, I have to say. And for the good fit, I have basically given you the method already. For this one, I haven't yet. Yep. Exactly. This is only for seen data points, and this is really for unseen data points. Yeah? That's already a good observation. So here you may have further knowledge that you want to bring into the game. Knowledge that's not part of your observed data. And we will talk about this. Especially fighting overfitting, we will bring in additional knowledge to make good predictions. And these good predictions will be worse fits to the data. We will fight overfitting. So not the same. And then we may be interested in uncertainties and significance, like doing confidence intervals and statistical tests. And and of course, depending on what you're interested in, for example, to do good predictions, you may change your original model to do exactly this. And that's what we also will do. By the way, so if we fit a plane or a hyperplane and just like the generalization into higher dimensional space, then we estimate the variance. The variance is supposed, or the noise is supposed to be normally distributed, and therefore, of course, the variance of y will have the same distribution. We said this already. And when we use this multivariate theorem, if we have a vector from a multivariate normal distribution, so here we have a normal distribution with a mean mu and a covariance matrix sigma, and we have such a vector C, and D is a matrix and V is defined, such that V is C plus the matrix times this vector, then our V is sampled from the normal distribution around this point, and this matrix D modifies the covariance matrix. And since we have estimated our beta hat by these matrices, we can apply the theorem. We just have to set our u to correspond to this y, our mu to correspond to our prediction, our sigma to be the variance, which is the same as the variance of our epsilons, and the v to be the beta hat, d to be this matrix that we have here. Then we find that not only our residuals are normally distributed, but also our beta are normally distributed. The nice thing is that the beta hat are normally distributed with the mean of the real beta. But they are normally distributed, so that means they are not exactly on the real beta. Or at least they could be in theory, but practically speaking, they never are. What this also means is that we have this covariance, and this covariance we can, with this theorem, describe eventually as sigma square and then x transpose x inverted. Just imagine this is a number, this x. Then obviously as this number grows, this variance is reduced. Well, we don't have a number, but we have a matrix. But as the matrix grows, we have more and more data observations. This term here becomes smaller. With more data observations, we reduce our variance. So the variance of our beta hat shrinks as we have more and more data observations. As we have more data observations, given that the assumptions are true, we get a better and better fit for our beta. So, as the variance gets smaller, the more data we have, the larger our matrix X is. The beta is normally distributed, yeah, with this. It just gives us knowledge about what if we start with certain assumptions. If these assumptions are true, what follows for what we have learned. So it's about an understanding of the process. This breaks down, of course, if our assumptions are wrong. And it tells us immediately that we have some nice properties of this learning process, like we see more data, we get closer and closer. And that's what we try to do in machine learning in general. Actually, there is something for which we don't have a lecture, at least not yet. It's called theory of machine learning. And there are a range of theorems that including that in good machine learning settings, the more data you have, the better you approximate the underlying truth. And here this is one special case, a very easy case, with linear regression, where this has been known from statistics for a long time, and where the theorem tells you more data from the same underlying distribution brings you a perfect representation as you go in the limit to infinity. Okay, so much for today. See you next Monday. Have a nice week.